So let's deal with the, today we are going to talk about the ideal quantum gas. So what do I mean by ideal? I mean non-interacting. Okay, so ideal means here non-interacting. And this really becomes, the quantum effects become measurable when the size of my box, say, is comparable to the wavelength, or when the density of the particle is high. You know, that's when the quantum nature kicks in. Now it turns out that there are two things that we need to take into account if you're going to deal with the ideal quantum gases. One is, what type of particles do we have? So the type of particle. So meaning that their spin, mostly their spin. Okay, so their spin, according to their spin, there can be two types of particles. Bosons. So bosons have, say, spin, integer spin. So if they can have spin 0, they can have spin h bar, they can have spin 2h bar, so on and so forth. And then we have fermions. And fermions can have half integer spin. So half of h bar, 3 halves of h bar, 5 halves of h bar, so on and so forth. Now the thing is, in nature, in everyday life, most of the fundamental, quote-unquote, fundamental particles that we deal with are fermions, with a little bit of a caveat. So, for example, an electron is a fermion, a proton is a fermion, and then a neutron is a fermion. But for example, if there are particles, so these are all fermions. But there are particles such as, which contain, say, an even number of fermions. They are usually bosons. So for example, helium-4. Okay, helium-4 has 2 protons and 2 neutrons. So it's actually a boson. But on the other hand, helium-3 is a fermion. Okay. And then there are photons. These are bosons. Okay. Now photons are a bit weird because, these particles in non-relativistic physics, apart from photons, these are all, their numbers are conserved. More or less. But the number of photons is not conserved. Photons do not have any charges associated with them. And also, since they're massless, their numbers are not conserved. So you cannot really you cannot control the number of photons by introducing a chemical potential. Okay, so photons are a little bit different. So this is one of the factors we have to take into account, is what type of particle do we have? Okay, the other thing that we have to take into account is the fact that fundamental particles, that quantum particles, are indistinguishable. Okay. So if two particles were to come into the same place such that their wave functions overlap, then there is no way for us to tell which particle is which after they leave that place. And that's something that has experimental consequence. Okay? So let's start by considering the two-particle wave function. So you've seen the Schrodinger equation. Now suppose that we had two particles. In that case, the Schrodinger equation will have the Hamiltonian, which will have the form of P1 squared by 2m, it could be a vector, plus P2 squared by 2m plus some interaction potential, say R1, R2. Now in our case, because we're dealing right now with ideal gas, so this is not there. So, so let psi be the wave function for a two-particle system. So these are two identical particles. So two identical particles, okay? Now suppose that we have an operator, P, which is the permutation operator, and what it does is that it just changes the two particles. So it changes the two particles positions. Then it is defined by this equation where it just exchanges the argument of the wave function. Okay? So this is how we are basically defining P12. Now, since the two particles are identical, this should keep the energy unchanged, right? So the energy should remain unchanged under this permutation. So this is another way of saying that the Hamiltonian should commute with the permutation operator. Okay? So we also expect the probabilities of the particles to be unchanged under this exchange. So which means that if I take psi R1, R2, and that should be equal to, and take its mod squared, that should be equal to psi R2, R1 mod squared. Okay. Did anyone have a question? Hello? There's also the back channel chat. You can use that.
Hello, sir.
Hello. Yes, Farhan, you had a question.
The V of R1 and R2, why does that become 0?
Because we are considering the case where the particles are free, so they're not interacting.
Oh, okay.
Yeah, I mean, because of the ideal quantum gas. I mean, what we're saying is actually so far is actually independent of whether V is, 0 or not. Okay, so now there are two possibilities that solve this condition. And I'm not going to in 3+1 dimensions. Okay? And those possibilities are, number one, that under exchange of the two particles, the wave function remains the same. In other words, the wave function is symmetric under the exchange of these two particles. So this sign is plus. Particles which behave in this way, these are, it turns out that they have to be bosons. So this is, they have to be bosons, and so boson, two-particle boson wave functions must be symmetric. And the other way is the particles do not, they have a minus sign. And particles which satisfy this condition have to be fermions. Okay? So this statement is a consequence of a very famous theorem called the spin statistics theorem. Okay? Now, it's weird, but let me just remark parenthetically, in 2+1 dimensions, there you can have a much more general solution to this equation. And the general solution is this. If you exchange the two particles, the wave function can change up to a phase that depends on the two particles, right? Because if I have a phase, then of course this remains unchanged, right? So, but this only happens in 2+1 dimensions, and particles where this happens, they are neither bosons nor fermions. They are known as anions. Physicists are really terrible at coming up with names. So yeah, I think it was Frank Wilczek who called them anions. And in condensed matter systems where you can have, you can, for example, have a system which is a two-dimensional, like a plane. So it's a 2+1 dimensional system. And then you can have vortices and stuff like that, which are kind of, not fundamental particles, but pseudo particles. And you can have an effective theory of these guys. And you can show that these particles will have anionic statistics. And anionic statistics is extremely rich because this has an interpretation of, you can do braiding, for example. So, if you have two anions and, and you exchange their places, then, you can like do knot theory with them. So there's a lot of very beautiful mathematics and physics that is related to anions. And I might just do a little bit of tutorial on it, but it's beyond the scope of this course.
Sir, are anions a totally new type of particle, or existing fermions and leptons or bosons are some kind of anions?
Well, they are boring type of anions where this phase is just either +1 or -1, right? Bosons and fermions. But in 2+1 dimensions, because we live in a 3+1 dimensional world, so anions in 2+1 dimensions are not fundamental particles. they are effective excitations, okay? So there's this idea of a pseudo particle where you have a system where you have an excitation that behaves like a particle down to some energy scale. Below that energy scale, they stop behaving like a particle, and you can see their more fundamental constituents. So from that point of view, anions are not fundamental. But there is no reason why, say, suppose there is in the multiverse, there's a 2+1 dimensional universe world. There is no reason why anions don't have to be fundamental. And if you have strings can have anionic properties, right? Because in 3 dimensions, suppose we are in 3 dimensions, so we have a universe, say, and the universe has, say, infinite strings going through it. So suppose, I mean, this is a very contrived example, but effectively, these can have anionic properties, right? And there, the anions are just going to be some sort of winding number. So anion, in that case, when this is what one string can wrap around another string, and in that case, the anionic statistics will have some interpretation of a winding. Okay, so I mean, there is no reason why anions don't have to be fundamental, but they cannot be fundamental in our universe. Okay.
Okay.
Okay, so before I move on, let me just give some names to these things. So this we call the symmetric wave function. And this is antisymmetric.